Welcome to Thermophysics Part 3. In this video, we're going to concentrate on gas laws. So we're going to start with a concept of gas pressure. We can understand the concept. There are three properties of gases that we're going to concentrate on here: temperature, volume, and pressure. So we're going to start with gas pressure so that we have an insight into the meaning of gas pressure. The first thing is, what is pressure? Pressure is defined as the force per unit area acting on the surface. You put a 20 newtons force on a 2 meters floor. You put a 20 newtons force on a 2 meters floor, then you have some pressure there. So the formula for pressure is force over area, but it's not going to be the main concentration on this part. So if you have been given a force and the area it's acting, you can just divide the area into the force, and what you're going to get is the pressure. The units for pressure are newtons per meter squared or Pascal. 1 Pascal is just 1 Newton meter per squared. So if you are solving a problem that has pressure, you have your force in newtons and your area in meter squared, then whatever value you are going to get, you can write it as Newton per meter squared or just Pascal with PA. So the pressure of a gas of constant volume increases when, actually, before we can even start discussing this concept, let me just give you an insight into the meaning of pressure. Let's say you have a gas trapped inside the container. How do you imagine the gas having pressure on the container? Remember, the movement of particles in gases, they are always moving about randomly, very fast. Because of those movements, they end up bouncing into the holes of the container. So that bouncing is like force acting on a unit area of the container, and that's pressure. So that's how the idea of gas pressure comes about. The rapid removing particles of gases end up bouncing or hitting the holes of the container. So that hitting is more like force acting on an area. So that's how the concept of gas pressure comes about. So the pressure of a gas, when the volume is constant, increases when, one, there are more molecules in the gas. So if that gas has got more molecules, then there's going to be more pressure, because more molecules are going to be bouncing into the holes of the container, are going to be exerting force on the holes of the container in a given period of time. The molecules move faster. So if the molecules move faster, then the pressure is going to be high. Remember what temperature does to particles. It increases the movement of molecules. It increases kinetic energy. So if you heat a gas, the molecules might even move faster. And if molecules move faster, then there's going to be an increased pressure, because there will be more bouncing or more force being applied to the walls of the container in a specific or in a specified period. Finally, the molecules have a greater mass. If the molecules have a greater mass, then the pressure is going to be high. You can see this to be greater mass proportionate to greater weight or greater force of the particles. So that weight or force implies that more force is being applied on a unit area, meaning that more pressure is being created. So these are the three factors that determine the pressure of a gas: the number of molecules, the speed of the molecules, and the mass of the molecules. So we're going to take a look at three laws that govern the three physical parameters of gases. We're going to start three physical parameters: volume, temperature, and pressure. So there are three different laws that govern or that tell us how these parameters are related. So the first one, sorry for the noise if there is any that you have heard. So the first one is called Boyle's law, and it states that for a fixed mass of a dry gas at constant temperature, the product of its volume and pressure is constant. So if you have a fixed mass, maybe 50 grams of dry gas at a constant temperature, maybe at 20 degrees Celsius, then if you multiply its volume and its pressure, what you're going to get is the same at any time. So what I'm trying to say is P times V, pressure times volume, will give you the same number at any time. So P is pressure in pascals or Newton per meter squared, and V is volume in meter cubed. So imagine a situation where you measure the pressure and the volume of a gas at two different periods. So at the first measurement, you get the pressure as P1 and the volume as V1. Then second measurement, you get the pressure as P2 and the volume as V2. So you have P1, V1, and at another time you have P2, V2. This states that if you multiply P1, V1, what you should get should be the same as what you can get when you multiply P2 and V2. So we can come up with an equation which is P1, V1 equals P2, V2. Pressure 1 times volume 1 equals pressure 2 and volume 2. So this equation is the equation that we can derive from Boyle's law. Let's take a look at an example. A gas occupies a volume of 2 meters cubed at 25 degrees Celsius and a pressure of 200 newtons per meter squared. What would be the volume of the gas if the pressure is reduced to 100 newtons per meter squared at the same temperature? So the temperature is the same, but here's what has happened. The volume, the pressure has been reduced. So what would be the volume if this happens? So we're going to say data, we have pressure 1, which is 200 newton per meter squared. We have volume 1, which is 2 meter cubed. We have pressure 2, which is 100 newton per meter squared. Volume 2, we don't have. So we're going to use the equation that we created. P1, V1 equals P2, V2. So let's plug in the values. So plug in P1, the first pressure was 200 newton per meter squared, right in pascals, times 2 meter cubed, pressure 200 pascals, volume 2 is what we're looking for. So we solve for volume 2. So we can divide both sides, or maybe we can first find 100 times 2. Then we're going to have 200 times 2. We're going to have 400 equals 100 V2. We can divide both sides by 100. So when we do that, we're going to have 4 meter cubed as the second volume. So this is how to use that equation. So next we're going to study something interesting about the Kelvin temperature scale. So when we started studying physics, we talked about the SI units of temperature. So the SI units for temperature are kelvins. Of course, we like using degrees Celsius, but the SI units are kelvins. So in most measurements, on most instruments, we are going to be getting a temperature in degrees Celsius. So that temperature has to be converted to the Kelvin temperature scale. So there are some funny or interesting facts that you need to learn about the Kelvin temperature scale. So the first is the smallest temperature possible is 0 kelvins, which is negative 273 degrees Celsius. It is said that nothing can exist beyond 0 kelvins mathematically. So using mathematics, their equations, you try to solve them, they are going to show that you cannot exist at a temperature beyond 0 kelvins. I won't go deep into that, but it's an interesting. As scientists, we say that atoms collapse beyond 0 kelvins. So this 0 kelvins is equivalent to negative 273 degrees Celsius. All right. So this temperature, negative 273 degrees Celsius or 0 Kelvin, is called absolute zero. So sometimes when they say absolute zero, just know they're talking about negative 273 degrees Celsius or 0 kelvins. So to change temperature from degrees Celsius to kelvins, this is the formula. So you get your temperature in degrees Celsius, then you add this 273. So if you have 0 degrees Celsius, you want to get temperature in kelvins, you just put your 0 degrees, you add 273 and you get 273 kelvins. So that's how it is here. So let's take a look at an example. Convert 0 degrees Celsius and 100 degrees Celsius into Kelvin. So here's the solution. So to convert 0 degrees, you just add 273 and you're going to have 273 kelvins. To convert 100 degrees Celsius, you just add 273 and you're going to have 373 kelvins. Next, we look at Charles' law. Charles' law. So this law states that the volume of a fixed mass of a gas at constant pressure is directly proportional to its Kelvin temperature. So here we have said the volume is proportional to Kelvin temperature at constant pressure. So in Boyle's law, we compared the volume and temperature. We kept the pressure constant. But here we're comparing the volume and the temperature. Sorry, let me just say that. In Boyle's law, we compared the volume and the pressure. We kept the temperature constant. That's why we had P and V. Well, in Charles' law, we compare the volume and the Kelvin temperature. We keep the pressure constant, meaning that we won't change the pressure. We assume that the pressure does not change. What happens to the change in the volume and the change in the temperature? So if the initial volume and temperatures are V1 and T1, and the final ones are V2 and T2. All right. So at the first measurement, our volume is V1 and our temperature is T1. And at the second measurement, the volume is V2 and temperature is T2. Then the following is true. But remember, your temperature should be Kelvin temperature, not the degrees Celsius temperature. So this is true. Volume 1 over temperature 1 is equal to volume 2 over temperature 2. Volume 1 over temperature 1 is equal to volume 2 over temperature 2. Here's an example. The sun heats 15 meter cubed of dry air at 27 degrees Celsius until its volume increases to 16 meter cubed under the atmospheric pressure. Calculate the temperature of the air. So the pressure was the same since they have said under the atmospheric pressure. So as the change was happening, the pressure was just the same. So calculate the temperature of the air. So here's the data. We have volume 1, which is 15 meter cubed. Temperature 1 is 27 degrees Celsius, which we need to convert to kelvins by adding 27 degrees Celsius, by adding 273 to 27 degrees Celsius, it will give us 300 kelvins. Volume 2 is 16 meter cubed. Temperature 2, we don't know. So we apply the formula V1 over T1 equals V2 over T2. Then we plug in 15, 300, volume 2 is 16, we're looking for T2. So we start solving. So when we do a cross multiply, we're going to get 4,800 and this side 15 T2. Then we're going to divide both sides by 15 and we're going to have 15 cancelling here, and 4,800 divided by 15 is going to give us 320 K. Remember, the temperatures we are dealing with are in Kelvin. Finally, we look at the combination of Boyle's law and Charles' law. So in this case, nothing is going to be kept as a constant. So we assume the volume, the temperature, and the pressure are changing. So this is the equation that combines Charles' law and Boyle's law. It says pressure 1, volume 1 over T1. Pressure 2, volume 2 over T2. This equation is called the general gas equation. Because if you can see, if you can master this, then you can be able to remember the Boyle's law and Charles' law. Let's take a look at an example. 15 meter cubed of a gas is at a pressure of 70 Newton per meter squared and at a temperature of 27 degrees Celsius. Find its volume when it is at a temperature of 127 degrees Celsius and a pressure of 35 Newton per meter squared. So here's the data. Pressure 1 is 70 Newton per meter squared. Volume 1 is 15 meter cubed. And temperature 1, 27 degrees Celsius, which if we convert is going to be 300 kelvins. Pressure 2 is 35 Newton per meter squared. Volume 2 we don't know. temperature 2 is 127 degrees Celsius. If we add 273, it's going to give us 400 kelvins. So 127 plus 273 is 400 kelvins. So we have our data. Next, we start plugging in. So P1V1 over T1 equals P2V2 over T2. So 70 times 15 over 300, 35 times V2 over 400. So when we do the multiplication on top, we're going to have 1050 and 300 on the bottom here. Nothing has changed. You can do, if you want, you can divide here, but you can also do cross multiply. If you do cross multiply, 1050 times 400 is going to give you 420,000. 300 times this is going to give you this. Then we can divide both sides by 10,500, and we're going to have V2. Of course, this side is just that I've swapped them. I've taken V2 this side, and the answer I got here, the other side, is going to be 40 meter cubed. So this is how to use the general gas equation, and this marks the end of gas